Hi, my name is Kiran and this is the final project presentation for the deep learning course. This is the 15-minute presentation and the topic of my course is adversarial neural cryptography. The problem of interest that we are trying to solve is if two neural networks can learn to perform cryptographic operations in the presence of a third adversarial neural network. With the advent of big data, machine learning, and deep learning, there's a lot of focus on data privacy, and a lot of organizations and individuals are sensitive that their data, personal data, might be leaked and they might be vulnerable. So, in this work, we determine if neural networks can learn to perform neural cryptography uh, automatically and hence protect information leakage in the presence of a third adversarial neural network. Most of this work is based on the paper and the results produced in the paper uh, titled Learning to Protect Communications with Adversarial Neural Cryptography by Martin Abadi and David Anderson of Google. The software and technology that we use in order to implement this project basically consists of a Python 3.6 version language framework. We also have the Anaconda package, the Jupyter notebook. We also have the TensorFlow package installed from Google, the Matplotlib, and we use Git to clone Google's TensorFlow research repository. The hardware environment for this project was basically a Mac OS desktop that I used. For this project, the data set was pretty simple and not too complicated to get. We generate this data set synthetically. The data set involves generating plain text data and associated keys. The plain text data is of lengths 16, 32, and 64, and we generate this plain text data um, using an uniform random distribution. Similarly, the size of the key is also of 16, 32, and 64 bits, and we also generate this key using an uniform random distribution. So these are the overview of steps that we took while implementing this project. The first one was to install Python 3.6, install Anaconda, install TensorFlow, and then I used Git to clone Google's research repository, and I was able to have a working workspace of all the Google's TensorFlow source code. So the schematic figure for for this particular project can be seen in this figure. Here, Alice and Bob are two neural networks who are trying to communicate with each other. Eve is the third adversarial neural network who is trying to eavesdrop on the communication between Alice and Bob. So here, the goal of Alice is to use the plain text data P and the secret key K and use them to perform some cryptographic operation in order to generate the ciphertext C. So Bob and Eve both have visibility to the ciphertext C. However, only Bob has visibility to the secret keys K. Eve does not have does not have visibility to the secret keys K. So both Bob and Eve are trying to recover the plain text data P from C. So here obviously Bob has an advantage because Bob can see both C and K, whereas Eve can see only C. So P Eve and P Bob are the reconstructed plain text data by Eve and Bob respectively. So the neural network architecture that we use for implementing this particular project is of type mix and transform. The first layer is a fully connected layer denoted by FC. It has as many inputs as outputs. Inputs to the fully connected layer is a concatenated vector of plain text P and the secret key K, which are of both length n. So we have a total length of 2n. The fully connected layer is followed by 4 convolution layers which learn to perform crypto operations as part of the training process. The final layer in this neural network architecture has number of outputs equal to n, and this final layer is connected to a tan nonlinear unit which scales the outputs in the range of -1 to 1 as is required for this particular project. So in order to perform the training and have the neural network learn how to perform neural cryptography, we need to define some loss functions. The loss functions are the functions that are minimized in the training period and used to optimize the parameters of the neural network. So in this particular case, there are different loss functions that need to be defined. The first loss function that we can define is the loss function for Eve. And this loss function measures the expected value of the error between the plain text, the actual plain text, and the reconstructed plain text as seen by Eve. Similarly, we have loss functions for Alice and Bob also. And then we also define a combined loss function for the whole network as LAB, which is equal to LB minus LE. And our goal is to minimize LAB. And LAB can be minimized by decreasing LB and increasing LE, as can be seen from this equation here. Here we show a snippet of the code that was used to implement this particular model in TensorFlow. The model consists of a fully connected layer FC, and then it has 4 convolution layers, and they are implemented using the code shown here. So to perform the experiment, we use various lengths of plain text P and the key length K. So we vary the length of the plain text to 16, 32, and 64. Similarly, we also vary the key length to 16, 32, and 64. The TensorFlow model that we use uses the Adam optimizer for optimization during the training period. We use a batch size of 4096. And here we show a snippet of the results generated when we run the program. It can also be seen in the command line here. So this command line is showing the results generated when the program is run, and the first column shows the iteration number, the second column shows the reconstruction error as seen by Bob. The third column shows the reconstruction error as seen by Eve. And remember that the objective of this neural network is to have 0 reconstruction error for Bob, whereas the reconstruction error for Eve should be maximal. And it can be seen that indeed Bob's reconstruction error over the training period goes down to 0, whereas Eve's reconstruction error during the training period remains high. So this is indeed a good result and what we desire from our neural network. We can also see that from the plots here. This plot shows Bob's reconstruction error as a function of the training iterations. And it can be seen that initially Bob's reconstruction error is high, but over the training period, the reconstruction error goes down and finally becomes 0. In the next plot, we see the reconstruction error for Eve, who is the adversarial network. And here we can see that Eve's reconstruction error remains high even as the training periods increase. This shows that Alice and Bob are actually able to communicate with each other while Eve is not able to eavesdrop on their communication, and hence Alice and Bob are effectively able to perform cryptographic operation on their transmitted data. So here are some of the lessons learned from this project. One is that running models takes lots of times. It takes hours actually. So it's necessary to start the project early, probably a month earlier, so that there's enough time to experiment. And that should help us to avoid last week or last minute issues. So in conclusion, it was proven that two neural networks, Alice and Bob, are capable of learning to perform cryptographic operations and communicate with each other in a confidential manner. Even if the adversarial neural network E can listen on to the transmitted data, it's not able to infer the actual plain text data from the ciphertext data. So this is indeed a good result. The stated paper has a lot more results and a lot more experiments that need to be performed. Also, the paper uses one kind of cryptography called a symmetric cryptography. It can be seen if this can also be extended to asymmetric cryptography. Thank you.